Good afternoon, well, good evening. So not sure if you are with your brunch or your dinner, but no matter where you are, no matter what you are doing, it's the time for CS202 operating systems. And not sure how many of you have paid attention to the song that we have played before, but some of you might heard it before when you were installing the Mac OS 10.5 Tiger. That was the song that you will hear during your installation process. And I believe most of the time when you click the button, start installation, then you are probably going to do something else to maximize your throughput. And today we are going to see how operating system would try to, well, I will say today is a lecture that you will see the evolution of the operating system design in a way that how we try to improve the throughput of executing programs. But before we start, it's always a good idea to remind you where you are, especially it has been quite a while since our last lecture. So again, we are saying about the big picture of computing is actually the von Neumann architecture in a way that a computer should consist of processor, memory, and storage in a way that we use the storage to store static programs, including instructions and data. And whenever we want a computer to perform a function, or say for the computer to run a program, we will have to load the program from the storage to memory, and then we will when the program start execution, then we will load the instruction from the memory to the processor itself, and the processor look over what instruction want us to do. Depending on the type of instruction, sometimes we may need to update the data, and sometimes we don't. And after we finish executing an instruction, we will update the program counter in a way that we will go to the next instruction, or an instruction that's in the branch target, and fetch the right instruction and repeat until the end of the program. So that's the big picture. So the big picture of execution is that a computer should consist of processor, memory, and storage. And the basic idea of your operating system is actually create an illusion that every program, every running program would exclusively own its processor, memory, and storage. So whenever you want to run a program, first of all, you still have your data, you still have your code in the persistent storage, and in the compiled code, there is a static data section. If you're interested, you can dump the program that's compiled by GCC on your Linux, and you will figure out that, well, every global variable that you declare during compile time would have its own space there. And then when you want to run a program, the operating system would create a virtual memory space, and the virtual memory space would consist complete 0 to 2 to the, for example, if you have a 64-bit address space, it will go through 0 to 2 to the 64 minus 1. And the whole address space is available for your program to use, no matter how many physical memory modules you install. You can freely use every address within the virtual memory. And the address usage looks like this. So in addition to the code and static data that you load from your persistent storage, whenever you execute the program, your program might create some local variables and some global variables. So if you have a global variable that dynamically allocated through function calls like malloc, then it would have its address gradually grow from the heap space, which is right after your static data section. And if you have local variables or arguments that you need for function calls or temporary storage within a function, they comes from the end of your virtual memory space, which calls stack. And the operating system, as we said, it provides a virtualized vehicle or say an illusion that you own this kind of a machine. So the operating system needs to track all of this for each process. However, as we mentioned, if we really want to track everything, then it's really slow. So the architectural support is that we divide the operations into user mode and the kernel mode. So if you are in user mode, then you are executing restricted operations in a way that we define a set of operations that if the program directly invokes these instructions, we believe it's safe and it won't affect other people's execution. And it won't affect the security of the system. So those instructions are restricted operations. They cannot modify the system states. And most of the time, your user processes will be in the user mode. However, when you really need to manipulate anything that's involved in a system level, oops, what's going on? When you need to, okay. Again, so when you need to involve in anything that's regarding the operating system level or say the hardware system level, then you will need to go into the kernel mode. And that's when the operating system will get involved. So this graph gives you an idea that most of the time you are in the user mode, which is the outmost ring in your privileged mode. And device drivers or kernel, they are operating in privilege mode, which and in fact, in most of the operating system, we have only distinction between the kernel mode and the applications. So the processor must support different modes to make this idea of privileged instructions working. And with this, we start to have the distinction between user process and kernel. So through the API, or say most of the time, your process will execute using those restricted operations that won't have your kernel code involved. However, whenever your process calling a system call, or there are some other operations, for example, exceptions or interrupt occurs, then that would trigger the kernel code to get involved. However, let's look at the system call case. If your process is invoking a system call, then it will use trap instructions to raise an exception in the processor in a way that the processor will save the current PC and jump to the corresponding exception handler in the operating system kernel. And this operating system kernel code will first save some of the register values to the memory and then handling your request accordingly and finally get back to you, your user program. And when you are executing the code on the right-hand side, or say the green box in our figure right on the right-hand side, you are in the kernel mode. So the kernel, well, a lot of you have the misunderstanding about it's a process. Actually, the kernel is not a process by itself. It works on behalf of the requesting process. So whenever your user process invoke a system call, then the process itself would set its PC to the involved kernel code, which is the corresponding system call handler that handles your operation, and then enters the kernel mode. So the user process itself will change its mode from user mode to kernel mode, and the process, the original user process, is executing the kernel. So in this way, the kernel itself is not a separate process. It's the user process, but the user process evolved from the user mode to kernel mode. So you can imagine if you are a diehard RPG game player, you know most of the time your character is really weak, but there are some cases that when you get some spatial item, then you can enter some kind of super mode or unbeatable mode, right? Something like that. So the kernel mode is exactly something like that. When your user process called a system call is like when you use that item, you can enter that kind of mode. And the kernel code will preserve the current architectural states and update the PCB process control block at the point. So as a result, you can imagine that whenever you call the kernel, you will have overhead. So that's why we say the kernel should be executed as little as possible, because whenever you execute a kernel, you are starting to slowing down your program. So we say this is a game show like live session. So the current standing is like the blue team scored 2 in the last lecture, but it's not a big big gap. So we believe the red team can do better today, right? So today we are going to continue our discussion on the kernel, because I do feel like there are more things we need to talk about on the kernel side. And then we are going to talk about the 2 research papers that has been assigned in your reading quizzes. So before we start, we say, well, we say the kernel should be executed as little as possible, but how big is the overhead of the kernel? So through my explanation, there are something that you need to do before executing the kernel code. And in the past, if you are an undergrad student, I would probably tell you the answer, how big the overhead is. But now, since you are a graduate student, I know I can give you some hints, and through the why and what the kernel want a system to do, you will be able to figure out how big the overhead and estimate how big the overhead is. So here is some number that I want to give you. So this is the latency number every programmer should know, and it's updated just before the lecture. It's the latest 2020 version. We haven't called it 2021 because 2021 we haven't made a new version. But for the 2020 version, here is what it looks like. So the L1 cache latency is about a CPU cycle. Branch mispredict is about 3 nanoseconds. L2 cache reference is about 4 nanoseconds. If you don't understand the first 3 lines, what we are talking about here, you definitely should take CS203 at some point. And I'm probably going to teach it again next fall if you can wait. And if you use CPU instruction to do locking unlocking, that would take 17 nanoseconds. If you want to send 2K bytes over the network, that would take 44 nanoseconds. If you want to reference the main memory, that will take 100 nanoseconds. If you want to compress data, that will take 2 microseconds. Read 1 megabyte from the memory, that will take 3 microseconds. Read 4 kilobytes randomly from SSD, that would take 16 microseconds. If you want to read 1 mega, that will be about 50 microseconds. And if you want to send a packet within the SAN data center, the round trip time will be 500 microseconds. And if you want to read 1 megabyte sequentially from the disk, that will be around 1 millisecond, and disk sync time is about 2 milliseconds. And if you want to send a packet from California to Netherlands, I have no idea why they use the Netherlands here. Maybe that's where the author is from, but it would take 150 milliseconds. So that's the whole picture of the latency number every programmer should know, and you should keep this table in mind, because later on we are going to ask you to do a lot of estimation on performance, and if you don't have this picture in mind, you will have no idea why this would take this long. And this is a version of 2016, and you can see some numbers are changing because technologies are changing all the time. And again, another thing that you will learn later is that, and as the technology changes, you may make different decisions in system designs. So that's why the why of operating system design is so important, because without knowing the why, you will not be able to make the right decision at the right time. So now, the question that I'm asking you is that, okay, so now knowing the table of latency numbers every programmer should know, can you tell me, like, if I want to perform a kernel switch, or say I want to invoke a system call, can you imagine how big the overhead is? Okay, that's rapid. Let's wrap up in 10 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so now looks like we are in a mode that we probably need discussion. And as you practice in the last lecture, the way how we do discussion is at first, you should open the file that I sent through the group chat, and then we are going to spend, for this question, I would guess 2 minutes on discussion within your group, and either the red or blue, one of your team member should, through the rest conditions, should raise your hand after the group voting is done. So now go ahead and discuss. landing your boat in 10 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so now I'm inviting one of the group to share your thoughts with us. So raise your hand. Okay, I have Xiang Yun. Xiang Yun.
Hello.
Hello.
I am from Team
Which
Blue.
team are you?
Yeah,
You
I'm
are in
from Team
blue.
Blue.
Okay.
Yeah.
Okay, what do you guys think?
So we think the answer is C, hundreds of nanoseconds, because
Okay, but
when
why?
when the OS switching from user mode to kernel mode, there are some context saving. So we need some mutex lock, unlock, and maybe some memory reference. So we reference the
Right.
17 nanoseconds and 100 nanoseconds to get the answer is hundreds of nanoseconds.
Right. So the right estimation here is about like hundreds of nanoseconds because you think you need memory references, right? But now some of you might say, well, this is just theoretical analysis. Well, that really, but thanks for your answer. But well, that really, is that really it? So now I'm going to show you a demo to let you know, is that really the case? So now let me share my screen. So if you want to know like what's the in a lot of the if you want to know the overhead of assistant operations, so there is actually a pretty good tool called LM Bench. And the LM Bench itself contains quite a few tools that can measure a lot of the latency of a lot of operations. And if you're interested, you can install this LM tool into your system, especially the Linux system. So here is the code of the LM Bench, and assume that I already compile, and you will see, because my system is the x86-64 architecture and it's Linux, so my binary is here. And now what I'm going to do is that I'm going to run a latency, the program called latency system call, because we say we are wondering for whenever you have a system call, you are doing a kernel switch, and we are wondering how much is your overhead. So here I set everything, every parameter to be just 1, and I try to repeat it 100 times, so you will have some idea about. So we take the average, so we can get the average number, so it won't be affected by a single system call. And there are a few system calls that you can do here, like null, read, write, states, f states, and open. But except for null, everything else would have some handlers code involved. So here I just want to do a null, so then you can see what's the pure overhead of doing kernel switch. So if I run this, right, it shows that a simple system call would take about 0.1543 microseconds, meaning that it would take 154.3 nanoseconds. So the answer is indeed about 100 nanoseconds in about a few hundred nanoseconds in this way, right? So now you know, well, if I understand what's going on, if I understand what's going on in the system, then it's so easy for me to estimate the overhead of our of the kernel switch in a way that you know it's hundreds of nanoseconds, right? So that's the power, how you should know the why of the system. If you know the rationale behind, it's not, you don't have to memorize it. All you need to know is that, well, it will need memory reference, so the number must be hundreds of nanoseconds, right? Or at least hundreds of nanoseconds. And I'm glad that you did the discussion, because if you look at, this is what we have before discussion. Quite a few of you think it's B, but after the discussion, I believe we got a majority, 88% of you are convinced the answer is C. right? So that's why we need this kind of discussion. So the main reason why it's hundreds of nanoseconds, because a majority of the latency comes from the hundreds come from the main memory reference. So now our question is that how does the processor knows where to jump to? So this is going to be related to what happens when you boot a system. So in the very beginning, when you power on or boot, uh, the basic input-output system, or say your BIOS on your motherboard, they have the consensus with the operating system saying that where in the persistent storage, most of the time your solid state drive or disk, where in the storage should you install the basic operating system kernel code. And then the operating system kernel code, they will have a set of they will have a table, and the table is called trap tables, and we will use privilege instructions that's actually part of the BIOS code to grab that table and then install that table in your system, and then and then we will put the system call handlers in the right place in your virtual memory, in your memory abstractions. And then after you finish install everything, it means that I finished the booting process. And then that's when we can start the first user process. And most of the time, your user process will be in user mode. But whenever you invoke a system call, then you will go back to the kernel mode by calling the system call handlers. And if your system call handlers will fork a new process, then you will have a new user process that's also in the user mode. However, whenever you call the system call, that user process will go back to the system call handlers on behalf of that user process, as we mentioned. So that's the whole picture of why the operating system code and your system, your process know where in the kernel code should I jump to, because you have the trap table installed when you power on or boot your system. And that's the whole booting process is trying to do when you power up the machine. So that's the whole picture of the modern, how operating system in modern computers would work. Now, that complete our discussion on the kernel part. And today we assigned 2 papers. I know you guys are suffering. I know you guys start to hate reading papers at this point, but the reason why I didn't tell you how to read research papers before this lecture is because I do feel like, people's memories, I just feel like it's kind of interesting. People always memorize things that suffers you the most, right? Like 2020, it must be the year, the most memorizable year in your whole life so far, because you suffer. You don't feel well, right? But you probably don't remember a lot when you are really happy. So that's how human brain looks like. So now I'm going to give you an experience like reading research paper is really hard. So then you can use that experience and you have a motivation. That's why I need to learn how to read research papers. So again, as I said, the whole the learning process, or say the learning, the things that you will learn in your life are actually categorized into 3 different parts: the why, the what, and the how. So again, so for each research papers, um, here's my take on it. You should try to figure out where are the whys, where are the whats, and where are the hows. And what are the whys? The whys is that for each paper, they should have a story to tell you why you should care about this paper. And it will tell you why we should have this paper in a way that the paper is addressing what kind of important problem. So that's the why. And the most important thing, that's actually the most important thing when you are reading or even writing a paper, because without the strong why, we don't care, right? We should, the paper should let you care why should give you an idea why you should be care about this paper and what's the problem about it, right? So that's the most important thing that you should learn the first when you read a paper. And then to address the problem that the paper is trying to do, what has been proposed. And that's actually, I would say, the second most important thing when you are reading or writing a paper. However, most of you, if you don't have the experience of reading a paper, you will spend a lot of time on the how. And what's the how? Is telling you how to accomplish the what's and how does the result of a paper looks like. And I would say they are the least important thing. And they are only important if you want to implement the idea. So the thing is that, right? If you are, so when you, and then after identify these three things, right? Uh, I want you to recap, like to think about, have I read papers that are related? And if they are related, why they have different approaches, right? So again, it's re-examine their whys and the whats. They may have different whys and whats, even though they seem to be related. And because they have some slightly difference in their whys, they would have completely different whats. So that's really important. And what will you propose? So if you are an engineer or you are a researcher, you should always thinking about like, what will I do if I am solving the same why? Will I do the same? Will I do differently? So that's another thing that I would like you to think. But at least, again, for reading a paper, you should understand the whys and whats. So, and why is it so important? Because as a researcher, you need to identify important problems. And by reading the whys, you will know, whoa, these are the important problems that I should spend my time. And you also want to know what has been accomplished. So then that's why the what parts becomes so important, because addressing these important problems, what has been proposed, so you don't have to reinvent the wheels. And some of you are thinking about that. Well, I'm not going to do research anymore. I'm just going to be an engineer. Again, as a lot of emails that I show you, as an engineer, you still care about the papers because you want to know, currently I am suffering from an issue. Is there a solution there already? Right? And again, if you want to know if there is a solution on the issues that I have been interacting, I need to know the why of the paper and what has been proposed. And based on the why, I would be able to know if this paper is related. And based on the what, I would know if this is applicable to my system. And so far, I haven't talked about anything about the how. So how is, again, the least important thing you should spend on reading a paper. And and you only care about the how is that after you identify the whys and the what, it's completely what I want. Then you should start care about the how. But before you pass the two stage of whys and what, you don't care about the how. So by just identifying the how, by just identifying the whys and what, you already get the whole idea of the paper. And that's really easy to do. So that's what I said. You can parse a paper easily by knowing by first figure out where's the why part, where's the what part, and where's the how part. And depending on how deep I need to understand about the paper, you can decide if I want to dig into the how or the what. So in this way, you can read a paper really quick. So now in the following lecture, I'm going to use the first paper, the structure of the THE multi-programming system, to let you understand how to figure out the why, the what, and the how of a paper. So this paper is written by Diestra. So not sure how many of you remember Diestra, but if you being a computer scientist, computer engineer who has been in graduate school for a while, if you don't know who is Diestra, it's a shame on you, because Diestra is actually a very distinguished computer scientist, and every of you who have ever taken a class called algorithm, you must heard about the single source shortest path problem, Diestra algorithm. That's by this Diestra. And if you took undergraduate operating system, you must know the synchronization mutex critical sections problem. And it's actually, if you spend a lot of time reading this paper, you will find them in in the appendix of this paper. It's also the contribution of Diestra. And if you spend all the time in the dinosaur book, you must know the dining philosopher problem, which is indeed the most inappropriate thing to do during the COVID-19 pandemic. But that problem is also designed and demonstrated solved by Diestra. And if you are in software engineering, the whole theory of verification of the program correctness is established by Diestra. The first person who talked about multi-threaded programming, concurrent programming, and a lot of other contributions are all by Diestra. So Diestra is everywhere in the computer science. However, the very first one of the very early paper that Diestra constructed is actually the paper that you read, the THE paper. So I know you spent a lot of time reading the THE paper. So now I am going to test if you can really capture the why of the paper by spending 90 seconds in telling me the answer of the question. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so according to the current answer, it looks like we really need some kind of group discussion. So go ahead, just open the files that I sent out through the chat and discuss within your group. Go. All right, let's wrap up in 15 seconds.
I don't see a prompt. Does anybody else have this problem?
Yeah, I don't see a poll.
Sure.
Yeah, me too.
Oops. Okay, here we go. All right, so try our best. So let me see. It's kind of, all right, so again, give me one more time. So for some reason, my software is not doing very well. Okay, so 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so now I am inviting one of the group to share your thoughts with us. Okay, so I have Rogelio.
Yes.
Hello. You
I'm
are in
Team Red.
red group.
We all agreed that the answer is C.
Okay,
Two.
but what are the two that you guys were thinking,
one
and why do you think like that?
Well, we chose 1 and 2, but the reason is because we ruled out. Okay, the first thing is we ruled out 3 and 4. The paper in the second page, it directly states it's not a multi-access system. Common data or data sharing is not supported. So 3 and 4 go out the window. And then the first paragraph on the first page, it states that, you know, we ultimately want to use economic use of peripheral devices, right? And then also reduction of turnaround time.
Okay, so
for programs.
So that's why you chose 1 and 2. So for other people, if you don't agree with what the red team is talking about, keep your hand raised. Okay, so Xingnan, you have different thoughts. Xian,
yes, I'm Xing'an.
Okay.
Our group thinks the answer is C2, but we don't agree. We think the answers 2 and 3 are correct, and
2 and
1
3
and
are
4,
correct.
1 and 4 are incorrect.
Okay, and how do you know this?
Because we think we ruled out 4 because and we chose 3 because we think the whole paper is about, you can see the keywords, multi-processing, multi-programming. So it must be something about multi-access system. So 3 is correct. And the reason.
So that's interesting, right? So so now, okay, remain unmuted, and I want to ask you, like, for this paper, I think Rogelio also have the same observation. So for this paper, where can we find a why? Where's the why of this paper?
Phrases in the abstract. After the abstract, keywords and phrases.
And Rogelio, do you agree with that?
The introduction, abstract, and the conclusion are good places for the why.
Okay, but if I just want to say, where's the why, right? Then this actually at the end of the first page for this red parts that I highlighted, the primary goal of the system is to process smoothly a continuous flow of user programs as a service to the university. And multi-program system has been chosen with the following objectives in mind: a reduction of turnaround time for programs for short duration, economic use of peripheral devices, automatic control of backing storage to combine with economic economic use of the central processor and the economic feasibility to use the machine for those applications for which only the flexibility of a general purpose computer is needed, but not the capacity nor the processing power, right? So these are the why they build a system. They want to build a system that's used for the university, and for the university to use, they have these 4 goals. And within these 4 goals, how many of the following fulfill the statements we have there?
2.
2? Xing'an, what do you think?
Could you repeat the question? I'm a little bit lost.
Okay, so look at the why, the red part, right?
Yes.
Do you see that?
Yes.
Right? And look at the question again, right? How many of them are coherent?
I think the first is correct. The first one must be correct.
Must be correct?
Okay. I'm not 100%
so how many
sure,
of you, okay, so how many of you read the textbook? Right? So there are some scheduling matrices, right? So CPU utilization is how, okay, put your hand down. And I know a lot of you read the textbook, right? So how busy you keep the CPU to be, that's the CPU utilization. And there is something called latency, that's the time between start executing and completion. There is a term called throughput, the amount of task process thread that we can finish within a given amount of time. Turnaround time, the time between submission arrival of the task and the completion. Response time, the time between submission and the first time when the job is scheduled. So look at the why, what the paper is talking about. Turnaround time, is that the same with the turnaround time? Is response time equal to turnaround time?
No.
Turnaround time, I think yes.
Is that equal to response time?
Could you return to the
What's the
page?
turnaround time?
Could you return to
What's the turnaround?
Turnaround time is the time between the first it is issued, then the completion. Yes, between
Right, but what's the
submission
response
and
time?
completion. A response time is the first time, the time between submission and it is scheduled. So for example, there are many shoppers going to a big
Right.
mart.
So here's the thing, right? So improving the turnaround time, does that necessarily mean that you are going to improve the response time?
No, no, no.
Right. So do you still agree the first statement?
No.
No, no, now, no.
So knowing the distinction, you will figure out the first statement is not correct. The second is also, the second is correct because we do mention the economic use of peripheral devices, right? But if you look at the following paragraphs, right? The system is not intended as a multi-access system. There's no common database, right?
Yeah.
And well, those are all the whys of the paper, right? And usually you should be able to identify the why in the very beginning part of the paper, right? But based on the why, you can easily identify, well, first of all, this is not a system that try to improve the response time. So if you're looking for algorithm to improve the response time, sorry, this is not a paper that you are looking for. If you're looking for a paper that tells you how to improve the utilization of peripherals, right? This paper would give you some ideas, yes, because it tells you how to economic use of peripheral devices. However, this is not a multi-access system. So if you are trying to design a multi-access system, this is also not a paper that you should be looking for. And if you are thinking about a paper that tells you how to perform efficient data sharing, unfortunately, this is not a paper. So I would say for this question, both teams, you didn't score anything because so you are so close. However, there are still some basic terms you have to be careful about. Like the response time is different from turnaround time, right? And if you look at the paper carefully, this is not a multi-access systems, right? So, but knowing the why, right? So we are just here. We just read the first page, right? Then we know, well, this is a paper that why people should care, because well, in the past, right, people think that, well, if I'm just having a short task, I want a computer to execute, do I need to wait forever? Right, so the THE paper is actually helping those people with really short programs. And you know, we are universities, and universities are really poor, right? That's why we charge you a lot of tuitions, and they pay those professors really bad, right? Because they are really poor, and I have no idea where they spend money for, but unfortunately, probably not computer systems. And that has been true since 1968. In a way that because we are really poor, so we want to make sure that our system can economically wisely use those peripherals, so the university can just spend one set of the hardware and to share it among multiple students, right? And automatically control a backing storage. Again, right? Why do you need automatic control? Because you want to save those human resources, and you want to economic use of the machine. And the last thing, which some of you already say that in conclusion, it also says why you should care about this paper, because this is actually the first operating system paper that trying to design an operating system in real and then tell you it's really hard. Designing a system is really hard. So this paper actually sets the foundation of the whole software engineering. So without this paper, there is no such a subject called software engineering in computer science. And this paper is saying that it's difficult to verify soundness, so we need software engineering. It's difficult to prove the correctness, so we need software engineering. And it's difficult to deal with the complexities of creating a system, so we need software engineering. And a lot of principles in this paper you will figure out is then part of the basic principles of software engineering. So some of you might feel a little bit of a headache about reading this paper, because this paper is really a grandfather old paper in a way that the computer is not a computer that you think. So right now, you know, our computer have processor, memory, and storage. But in the era of the THE, well, they have the processor, but if you look at the clock rate, it's kilohertz. It's about, it's really slow in a way that it's probably 500 times slower than your current, well, not 500 times. It's actually 5,000 times slower than your current processor. And the memory is called core memory, and the storage is called DRAM. So and the order of magnitude of measuring the capacity is also completely different. Like at that time, the clock rate is in kilohertz, and at that time, the memory only has the capacity of kilobytes, and at that time, the DRAM only have hundreds of kilowords storage, and the response time is a lot slower than what we have today, right? So that's the era of the THE. And because they are dealing with that kind of computer, you might feel that the way how they design a computer system is a little bit different from today. And based on the whys they propose, there is a what. That's right after the why section. They tells you what we propose. So the first thing they propose is a hierarchical system, and they propose pages, they propose processor allocation. So that's what they proposed, right? And restricted layer design, that's actually the first thing they proposed. And to deal with the processor allocation, they have the abstraction of processes. And later on, they tell you detail about what's inside each restricted layer design. Like at level 0, they find the responsibility of the processor allocation in there. And the level 1 is segment controller, control the usage of your memory. And the level 2 is message interpreter. And the level 3 is in IO buffers, and the level 4 is the independent user program. And level 5, we didn't mark it here, is say it's the operator, but it's actually the joke. So don't take this the level 5 seriously, because that's actually some kind of humor in that era. But but the restricted layer design on the system part, it only has 5 layers. So this is what they have proposed: the layer 0, processor allocation and scheduling. And with that, they propose the abstraction of process. And layer 1 is the memory management, and that's where we start to see the shadow of virtual memory. And layer 2, that's the message interpreter. And layer 3, that's the IO buffering. Layer 4, that's the applications. And layer 5, that's you, the operators. And so this paper actually, first of all, it demonstrates that the idea of virtualization, so virtual process, virtualized processor, virtual memory, and message interpreter, you can consider this as some kind of virtualized console. And all other devices, they have to be virtualized to deal with the virtualized, to interact with the virtualized console and applications, right? So each layer has a different privilege mode. So if you really want to support this kind of system, your processor actually need like 5 levels of execution mode. But if you look at the modern processor design, we only have 4 different layers, right? So apparently later on, we abandoned this kind of design. But at this point, at least you know each layer needs different privilege mode, and your processor at that time, you need to provide this 5 different levels of execution modes, and each mode has its own meaning, right? So now I'm asking you, why Dijkstra at that time they think the hierarchical layer design is a good idea? All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so for this question, I saw so far we have a pretty good consensus of an answer. But to prevent a case where we just saw that, well, both the team think the answer is that, but they have different ideas among these 4 statements. So I still want you guys to have a quick and short discussion, maybe for 2 minutes, to synchronize your thoughts. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so after discussion, I saw there are some shifting among the answers. So now I'm inviting one of the group. Well, just raise your hand to tell me what the group discussion have been telling you. So wait, the first one that I have is actually Xing Yun.
Hello.
Xiang Yun. Xing Yun.
Xing.
What do you
Okay.
think?
The result of our group discussion is 3. In detail, the option 1 and 2 are correct, and 3, 4 are incorrect.
Okay, so which one do you think is correct?
Option 1 and 2, the debugging and verification is mentioned in the paper. And for option 3, my reason is because this hierarchical design is there are many layers, but if we just want to do some specific operation, maybe some layers are unnecessary, so it will introduce some extra overhead. So see,
so another thing to think about, like the demo that I just showed you, right? As I said, whenever you need to change the mode of your execution, right? You need, well, if simply just kernel switch, it takes about, like, with modern processor, it already takes about like hundreds of nanoseconds, right? And at that time you just saw it's so slow in the memory, right? So, and you have 5 layers, right? So if I want to change the processor allocation, then I have to do like 1, 2, 3, 4 switches to reach layer 0, right? So that would take a lot of overhead. right? So it's definitely having more overhead than just having one layer, right? And how about 4?
The I/O and peripherals are in layer 3, which is higher than layer 0. So I think it's wrong.
Right. So another thing is that because layer 0 and layer 3, they are separated, right? So it's like your peripheral is not in layer 1. So layer 0 actually cannot directly interact with that, right? So it actually would occur some potential issues in the system as well. Is that what if so there are quite a few issues here, right? So if my processor or say the scheduler needs more memory, right? If my processor wants to access the I/O, right? There's no way you can do that because of the strict layering, right? And because of the strict layering, it is always your memory is always the upper layer can request the lower layers. So there's no way for layer 0 to request more memory from layer 1, right? So this strict layer design has its own potential problems. So Tyler, do you have anything you want to share? Okay.
No,
If
sorry, I
not,
just
then
forgot to unraise
oh
my
no,
hand.
that's fine. Just want to make sure. All right. So if everyone is okay with that, we agree that we agree that, right? We agree that for this question, right? 2 of the statements is not correct, and the 4th statement is also pointing out a potential design issues in the system that because you have the strict layering, right? So, and the peripherals always need to go through the message interpreter, and there's no way for your layer 0 to request to control the I/O directly, peripheral directly. There's no way your layer 0 can access more memory, right? So turns out, if you look at the paper design, it says that this operating system only supports at most 5 processes. The reason is just because we know the processor the layer 0 cannot request more memory. So we have to make sure that every program can execute without any issue. So we can only conservatively saying that the system can only support up to 5 processes. So this operating system, although it supports concurrent execution, but to a very limited degree, 5. And that's because of the strict layer design. However, this paper has a lot of hows, which at this point, we don't care that much because we already know the high level idea. And the how here, like how can we share the peripherals is the mutual exclusion, right? And the appendix has the detail and of the mutual exclusion. But knowing the mutual exclusion in detail doesn't affect our understanding about the paper, right? So to understand what the paper is talking about and why they care about this paper, the how is not that important. It's only important if in a way that you want to implement mutual exclusion, then you care about what they are doing. Otherwise, we are done with the paper, right? And how they achieve their goals, they build a layer system. They have the priority scheduling, but the detail of the priority scheduling only if you are interested about how they improve the turnaround time. We don't care, right? The mutual exclusion is used for sharing resources, and that's why they have the mutual synchronization, right? And it's used for processor allocation, access the physical console, access peripherals, and later on we will discuss the mutual exclusion, but not now, right? But at this point, we already know that here's the goal of the THE system. And what else? And the paper, as I said, this paper is influential, but not in operating system perspective. You will see a lot of hierarchical design still. in networking, you have the physical layer, link layer, network layer, transport layer, application layer. That's a strict layer design. And the link layer can only interact with the physical layer. Network layer can only interact with the link layer. That's exactly like the Dijkstra's paper. And so you can see there are a few impacts about the THE paper. So it has the process abstraction. It has the hierarchical system design. First paper proposed the hierarchical system design. And the whole reason why they want a hierarchical system design is they want to facilitate debugging. And the reason why networking use the hierarchical system design is also because they want to facilitate the debugging and testing. And it's also the first paper mentioning the idea of virtual memory. And it proposed the influential mutual synchronization algorithm, which make a lot of you suffers in the undergrad operating system. But as a graduate operating system, we don't care about those house. It's only useful when you want to implement those mutual synchronization yourself. So at this point, we are done with the paper. And now I'm going to navigate you through the second paper, Hydra, the kernel of a multiprocessor operating system. And but for this paper, I feel, as I said, right, when we read the paper, we always want to compare and relate this paper with the paper that we have read before. So for this paper, because we want to compare, so I want to talk about the what's first. So the what's of the paper you can find in its design philosophy. So it's interesting to see their design philosophy, and they are pretty different from Dijkstra. So it's a multiprocessor environment. It's proposed the idea of separation of mechanism and the policy. It integrates the design implementation methodology and rejection of stricted hierarchical layering, protection, reliability. So those are the what's in their design philosophy. And the most interesting thing is the fourth one. So why they propose the rejection to strict layering. Let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so for this question, we don't need the group discussion, but if you raise the hand, you can still score 1 point for your group. So I invited one of you to raise your hand. So I have Rogelio. You are the red team, right? So
Yes,
what do you think?
I believe the answer is D, improve flexibility.
And why is that? Where did
Uh,
you find it?
I found it in the second page under number 4, where it says, so it says,
right. So the Hydra paper, right? So it's actually saying that they want to construct an environment and for flexible and secure operating system, right? So that's why, okay, so red team scored 1, yay, right? So, and thanks Rogelio. So the reason why we care about Hydra is that, well, the Dijkstra's paper already talked about the hardware efficiency and utilization, but we want to make it better. And the other thing is that how dare are they in rejection the idea proposed by Dijkstra is actually because strict layering is not flexible, right? As I just showed you, right? For the strict layering, because the layer 1 and layer 0, layer 0 cannot request resource from layer 1. So there's no way a process can request more memory. So it turns out that you have fixed number of processes, and your operating system has no way to control your peripherals. And turns out that well, your layer 0 has no way to allocate more resource for peripherals or whatever, right? So it turns out that it's not flexible enough, right? So to fulfill the first requirement of flexibility, they have to reject the idea of a strict hierarchical design. And for the security, they are the first paper proposing the idea of protection, which we will talk about later. But the main reason why we should care about the paper is because they want to propose a system with security and flexibility. And turns out that for the flexibility part, the rejection of strictly hierarchical layering is actually the main point. And you can see they have a lot of things in caring about the flexibility in a way. They want to support multiple processors so that you have the flexibility of using multiprocessor hardware. They separate the mechanism and policy for flexibility's perspective. And they have the protection, they have the reliability for the security. So that's what the paper is proposed. And what they are proposing is actually addressing the two words, flexibility and security, that's in their whys. So whys are so important, right? And it's also a paper that have a clear definition of a kernel. So in their kernel, they are an abstract. The kernel is an operating system defines an abstracted machine by providing facilities, resources which are more convenient than those provided by the bare hardware. And an operating system allocated resources in such a way to most effectively utilize them. So this is what the kernel should be doing in operating system. And this is also a paper that have a clear definition of what the kernel should do at least. So they tell you exactly the kernel is aiming at providing an abstracted machine, which is the virtualized environment, or say a process. And the kernel allocates the resource, schedule them. So that's the whole idea of the kernel of an operating system, right? So, if you look at the design of their paper, right? So for the THE paper, they have the restricted hierarchical design. So whenever you need to switch a mode, you have to cross the privilege boundary. And previously, as you guys mentioned, whenever you cross the privilege boundary, there is an overhead. For Hydra, it's only the distinction between kernel and user processes. So the overhead and the flexibility are significantly improved. So that's why Hydra decided to take a completely different approach in terms of the operating system design. We will continue the discussion on Hydra in the next lecture, but there is a reading quiz due this Thursday, so don't forget to take that reading quiz. It will be available 10 minutes after the lecture. Other than that, enjoy the rest of your night, and I will see you on Thursday.